Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends so that they can also explore my channel. And that's the only way you can help me promote my channel, refresh me and inspire me. So here we go. This is about criteria for maxima for beams due to unequal concentrated live loads at distance h apart. Actually, I already discussed this, and this was also discussed in the mechanics of materials. So let's have it again here. The idea is for maximum reaction, put the heavier load over the support and the lighter load on the span to maximize the reaction as shown. And we base also it to the influence lines. So remember that for maximum reaction, this is the influence line and the value of the ordinate over the support is 1.0. So therefore, because this is the maximum ordinate, the heavier load should be placed over that support and the lighter load should be placed on the span. So there are two ways to derive Ra max. One is using the influence line by computing the ordinate under the lighter load here in terms of H and L. The other one is apply statics, you sum up moment about B. The results would be the same. So I'll just apply using the ordinates to the influence line, and this is y as to, this is L minus H equals 1 as to L. So y is L minus H over L. So that Ra max is pH times 1 or pH plus PL times quantity y, and y is L minus H all over L. So plus PL times L minus H all over L. So Ra max is pH plus PL times y, or in particular Ra max is pH plus PL times L minus H over L. Do not memorize, just base it on the principle, position the loads, and from there you can compute Ra max into two ways. One using statics by summing up moments about B, the other one is by the influence lines. So PA sub H is the heavier live load and P sub L is the lighter live load. Maximum shear at a point. So let's have the influence line. Remember, this is the influence line for shear at point C. For example, this is C. This is negative A over L, and this is B over L. Now, if B is greater than A, B over L would be greater in magnitude than A over L. Therefore, again, based on this influence line, the heavier load should be over B over L, and the lighter load should be on this portion of the segment that B. That should be the arrangement. However, if A is greater than B, then the heavier load should be over A over L, and the lighter load should be somewhere here, because the movement would be reversible, just like in bridges. So for this case, this is B minus H, so therefore V sub C max is PH times B over L plus PL times the ordinate here, which is B minus H as to, if we extend this, this is B definitely as to L. So B sub C max equals PH times B over L plus PL times B minus H over L. So I want you to derive this, derive the ordinate here, and show that it is B minus H over L. Or the other way, V sub C max is equal to RA. So this is the positioning of the two loads. Solve for reaction at A, then you can find that V sub C max is equal to RA minus V sub C max equals 0. So this would be the expression of V sub C max. But do not memorize. The principle is the same. Just position the loads. After that, you can analyze by statics or by the influence line. Maximum moment at a point. So we recall the influence line for moment at C. It looks like that, and the ordinate here is AB over L. So therefore, because this is the maximum ordinate, we place the heavier load over it, and if V is greater than A, the lighter load somewhere on this segment. And again, if we base it from influence line, you just compute the ordinate to the influence line here. Then it is PH times AB over L plus PL times whatever the ordinate here. The other way is to compute for RA. Then after this arrangement, summation moment about B, having found RA, then you can compute the maximum moment at C as RA times A. That's the other way. So if we base it from influence line, I'll call that Y, and remember this is B minus H. So B minus H has to, or Y has to B minus H equals AB over L has to B. So A over L, therefore Y is B minus H times A over L. So Y has to B minus H equals AB over L has to B. So Y is A over L times B minus H. Therefore, the maximum moment at C due to two concentrated moving live loads is PH times AB over L plus P sub L times A over L times B minus H. Again, do not memorize, base it on principle, although that's the formula. I don't want to apply this formula. I want you to base it on principles, how to position the loads, and apply two ways. Either the influence lines and the influence diagram by deriving the ordinate under the lighter load, and the second one is by statics. You compute for RA. After solving for RA, you cut section C, then maximum moment at C is simply RA times this distance A. MC max is RA times A. So that's it for this part. So fourth, absolute maximum moment in a beam due to unequal concentrated live loads. So I already discussed this, and remember the principle that for absolute maximum moment, it occurs under the heavier load for two unequal loads, but applicable also if they are equal when that load and the resultant of the loads are positioned equidistant from the center of the beam or girder. So that should be the positioning, and the resultant of the two loads is, let us say, R, and R is PH plus PL. The center between the heavier load PH and R is the center of the beam, recall. We will call that X, and this is also X, the distance of R from the right. And if that's RA, this is the center line, then the distance between the heavier load and R is denoted by E. So therefore, the distance of PH from the center line is E over 2, as well as from the center line and R, it's also E over 2. So therefore, this is L over 2, because it's the center line. That's E, and E over 2, E over 2. So X is L over 2 minus E over 2 from the figure. It is where absolute maximum moment occurs. So X is L over 2 minus E over 2. Another way to compute maximum moment, absolute maximum moment based on statics is you compute Ra by this positioning, then you just take moment about this point, and M absolute max is Ra times x, where x is L over 2 minus E over 2. So M absolute is Ra times x, and let's derive that. So Ra times L, summation moment about B equals 0. Ra times L equals R times x. So Ra is R over L times x, which is L over 2 minus E over 2. M absolute is Ra, this one, times another x. So therefore, M absolute is R over L, L over 2 minus E over 2 quantity square. Because we have another x here. So simplifying further, M absolute is R over 4L, quantity L minus E quantity square, where E is, by Varignon's theorem, R times E equals PL times H. Again, R times E, we consider this as our reference. By Varignon's theorem, R times E equals PL times H. So therefore, E is PL H over R. Substitute here to have a specific formula. So take note that R is PH plus PL. So the value of E is PLH over R. We can replace E here by PLH over R to make it more specific. So let's derive this in here. Now we have limiting value of the span L sub M, so that two load condition yields absolute maximum moment. So depending on the length of the span, there is a possibility that if the length of the beam is shorter than this limiting value L, there's a possibility that the lighter load will be off span. When we arrange PH and R, it will be off span, so that one load, only the heavier load over the span, especially at the center, will give maximum absolute moment. So let's derive this L sub M. So the idea therefore is we equate the absolute maximum moment when there are two loads on the span to that of the absolute maximum moment when there is only one load on the span. And for that to be absolute, it should be the heavier load at the center. So moment absolute when there are two loads equals moment absolute when there is only one load. This moment absolute when there is only one load is P heavier L over 4, remember, when it is at the center. While if there are two loads, this is the formula, we just replace E by PLH over R. So R over 4 L sub M, based on this formula here, when there are two loads, times quantity L sub M minus E, which is PLH over R. I now replace it. Quantity square equals, when there is only one load, it is PH LM over 4. We cancel 4. Then we have R times cross multiply LM there. So R over LM equals LM minus PLH over R square equals PHL. Cross multiply LM to the right. So R times LM minus PLH over R square equals PHL square M. So extract the square root. So we have square root of R times quantity LM minus PLH over R equals square root of PH L sub M. Then distribute square root of R LM minus PLH over square root of R equals square root of PH L sub M. Then this negative transposed to the right, common LM factor out. So Lm times square root of R minus square root of PH equals PLH over square root of OR. We replace P sub L equal to R minus PH. So quantity R minus PH, H over square root of R, and we express this as square root of R minus square root of PH times quantity square root of R plus square root of PH, like that. So we can cancel square root of R minus square root of PH, and L sub M equals square root of R plus square root of PH quantity times H over square root of R. Then square root of R over square root of R is 1 plus square root of PH over square root of quantity PH over R times H. Therefore, the formula for LM is it is equal to quantity 1 plus square root of PH over R times H. So that's the limiting value of LM, so that two-load condition yields absolute maximum moment. So in other words, when L is greater than case 1, when L is greater than LM, then two-load condition gives maximum absolute maximum moment, and the absolute maximum moment is given by R over 4L quantity L minus PLH over R quantity square. So that's the formula, but do not memorize. You can derive this again if you want, based on this principle, that absolute maximum moment is simply RA times X, and X is L over 2 minus E over 2. Then when L is less than LM, then that means one load condition gives M absolute max, and the absolute maximum moment is given by PHL over 4. And finally, when L equals LM, then either load condition gives absolute maximum moment. So that's it for this situation. So to verify the principles discussed in the preceding slide, let's have this example 65-C. Two loads each 20 kilonewtons and spaced 9 meters apart. So this is H. P heavy equals P light equals 20 kilonewtons in this situation. Move on a simply supported beam. Compute the absolute maximum moment in the beam if the beam is 12 meters long, 15.36 meters long, and C 20 meters. So first, let's solve for LM. And L sub M is given by quantity 1 plus square root of P heavy over R times H. Remember the formula. So substitute LM equals quantity 1 plus 20 over R is 40, 20 plus 20, there are two equal loads, and times 9. So L sub M is 15.364, this value here. So therefore, because L is less than LM, then one load condition controls, and the maximum absolute moment is simply P heavy L over 4. So substitute 20 times 12 over 4, M absolute. So it is 60 kilonewton meter. So that's the answer for the first case. For letter B, let us show that the absolute maximum moment when there is only one load is equal to the absolute maximum moment when there are two loads. So in this case, M absolute is 20 times P heavy, which is equal to P light, times L 15.364 over 4. So it is equal to 76.82 kilonewton meter. If you use the other formula, where there are two loads, so it is R over 4L quantity L minus P L H over R quantity square. So R is 40, L is 15.364, H is 9, P light is also 20, and R is, as I said, 40, L is 15.364. Substitute 40 over 4 times 15.364 times quantity 15.364 minus 20 times 9 over 40 quantity square. So M absolute is also 76.82, which confirms the principle and the theory. Then finally, L is 20 and 20 is greater than L sub M, therefore two load condition controls. So we use this formula for absolute maximum moment, and it is 40 over 4 times 20, quantity 20 minus 20 times 9 over 40 square. So M absolute equals R over 4L, quantity L minus PLH over R quantity square. So 40 over 4 times 20, quantity 20 minus 20 times 9 over 40 quantity square. And it gives us a value of 120.125 kilonewton meter. So these are the absolute maximum moment for these different cases.